So section 4 is the calculus of variations. This is the final section of the course. Let's go through these notes. So you're familiar from calculus, from sort of regular standard calculus, with the problem of maximizing or minimizing a function. Okay, it's very simple. As you know, you're given a function. Y is a function of x. And you want to know where that function is a minimum or where it's a maximum. So what do? Well, there's a simple recipe. You take the derivative of y with respect to x, and you set it equal to 0. Now, y is a function of x. Y primed, the derivative, is also a function of x. So y primed equals 0 is a problem where you solve for x. You know what y prime looks like as a function of x. You set that equal to 0. You find a value of x, and that's the location of the minimum or maximum. And you can substitute in that value of x back into y to determine the actual minimum or maximum value of y. To determine whether or not you have calculated a minimum or a maximum, well, you could do something like calculate the second derivative, look at the sign of the second derivative to determine whether you have a maximum or a minimum or an inflection point. Okay, so this is all very familiar to you. The basic idea, though, is you want to find one value of x that gives an extremum value of y. Extremum just means maximum or minimum. Okay, so you know all that. You've done lots of problems in your calculus courses where you maximize or minimize functions. Okay, but now what we want to do is to consider a very different kind of extremum problem. Similar in a way, but it's fundamentally different. So to explain what the problem is, or what kind of problem we're going to consider, I want to use two illustrations. Okay, the first one goes by the name of geodesics. And what's a geodesic? A geodesic, well, you'll see what it is. So let's say you have 2 points. Okay, the first point is in the xy plane. So 2 points. One is at x1, y1. And the second point is at x2, y2. Okay? And we want to consider a function that joins these 2 points. Okay, now, I have a figure over here. Okay, so not the bottom part, the top part, the geodesic figure over here. So here's the point 1, here's point 2. And if we have a function, the function could be this red curve, or it could be this blue curve, okay? You know how to calculate the length of this curve going from point 1 to point 2, okay? So the way you do it, the way you're going to do it, is you use this fact here. If you take an infinitesimal section or length along, let's say, that red curve, call that ds. Okay, you construct a right-angled triangle where the projection on the x-axis is dx, the projection on y is dy. And obviously from the Pythagorean theorem, ds is equal to the square root of dx squared plus dy squared. Okay, so you know that. Okay, so that's this statement here. ds squared equals dx squared plus dy squared. Or ds is the square root of dx squared plus dy squared. You can factor out the dx, okay, and when you do so, you'll have the dx times the square root of 1 plus the square of the derivative dy by dx, okay, which we can call the derivative y primed. So the total length of the curve is going to be the sum of all these little bits of section of the curve, the sum of all the bits that go from point 1 to point 2. So you imagine this ds is just a little tiny piece of this curve. You sum all the sections from point 1 to point 2. You sum all those lengths, and you get the length of the total curve. Okay? So you've probably seen this in calculus. You've probably seen this equation before. So the length is going to be an integral of dx times the square root of 1 plus the derivative y primed squared. Okay, you know all that already. So if you have a function y of x, if you know what this function is, you can calculate the length of the curve going from x1 to x2. Okay, point 1 to point 2. But what if we were to ask this question? Tell me the function that minimizes the length. Okay, so I use the word minimizes here, so you know that this is an extremum problem. But it's a very different kind of problem from the standard one in calculus that I talked about a little bit earlier on the previous slide. Okay, because I'm not asking for a value of x that minimizes or maximizes a function y, a known function. I'm asking, what is the function that is going to minimize this definite integral? Okay. Well, if you think about that, you probably realize you don't know how to answer this question. Okay, but we will find out how to answer this question. Let's leave that for the moment. Okay, so that's an example of an extremum problem that I want us to be able to solve. Here's a second one. It's called the brachistochrone problem. And this is a word that comes from two words in Greek: shortest time. Okay, so what kind of problem are we considering here? Okay, let me go back to this figure. So forget about the top part, just look at the bottom part. Let's say I have an x, y axis coordinate system. For convenience, I put the y-axis pointing downwards. And again, I have 2 points, point 1 and point 2. And I'll choose the x and y values of point 1 to be 0 and 0. So we start at the origin of the coordinate system. x2 and y2 is something. I haven't specified what it is. But let's say I do specify this. So I know the beginning point, I know the final point, and there's a function that connects these 2 points. Okay? So imagine what this function is. It's a surface. Okay? And you put an object up here, and this object slides down along this surface. Okay? So again, this is a surface. We're going to make it a frictionless surface. Think of it as a track, or a track or a surface that an object can slide down. And here's the question. What is the function f of x, which describes the shape of this curve, that will minimize the time it will take an object to start at point 1 and finish at point 2? Okay, you got that? So you start up here, you follow this track, which is defined by the function f of x, y equals f of x. You end at point 2, and you want this function to be chosen so that it gives you the minimum time to go from point 1 to point 2. Okay, so again, a particle slides down that curved track, starting from rest. First point is the origin. The end of the track is another point that you specify. F of x is the function. Y points downwards. Let's use conservation of energy here. So let's say the particle, the object, starts from rest. Okay? So its initial energy is, kinetic energy is 0 because it starts from rest. The gravitational potential energy is also 0 because y at point 1 is equal to 0. So mgy is equal to 0. Okay? And you'll notice we have a negative sign here. I have a negative sign, negative mgy instead of positive mgy. Remember, because the y-axis is pointing downwards. Okay, so as y increases, the object falls, and the gravitational potential energy decreases. Regardless, they're both equal to 0, so the initial energy is equal to 0. Now, conservation of energy says kinetic energy plus potential energy, so is constant, and that constant is equal to 0 because it started at 0. So y is any value of y. V is the speed of the object at that value of y. If you solve this equation for v, you get v, the speed, is equal to the square root of 2g times y. Okay. Now, the time it takes for the object to move a distance ds along the track, okay, so that's an infinitesimal distance, is going to be the distance divided by the speed. Okay, well, here's the expression for speed in terms of y. But look, we also have an expression for ds. If you go back to the previous problem, we have ds is equal to dx times the square root of 1 plus the square of y primed. So I use that equation as well as 4.3, so equations 4.1 and 4.3, and I find that the time, the infinitesimal time it takes to go this distance ds, is given by this expression, dx times the square root of numerator divided by denominator. And then we say, okay, how much time is it going to take to go from the origin, the first point, point number 1, to point number 2? Okay, well, what I need to do is add up all the bits of time, dt, that it takes to go all those infinitesimal distances. I add them all up. That will give me the total time. I call that capital T. Well, adding them all up means doing an integral. And our independent variable is now x. X goes from x1 to x2. So here I have an expression. I have an expression for how long it's going to take this object to go from point 1 to point 2. Okay? And I have it in terms of an integral, and I have the integral, or the integrand, written in terms of the function y and its derivative. Now, if you know what the function y is, if you know what this function is, great, then you can calculate the time. But what if I were to ask the question, what function is going to minimize the total time taken between those, for the object to go between those 2 points? Okay, it's a similar kind of problem to the geodesic problem. Similar kind of problem because it's a extremum problem. Okay, in this case I'm asking for a minimum. But what I'm asking for specifically is an unknown function. What is the unknown function minimizes this total time? Okay, so that's another example of an extremum problem that I want to consider. So, how are we going to approach this? Okay, this is going to take a little while to go through. We're going to derive something called the Euler equation. Okay, I'll do that in the next screencast, but let me just skip down to the final result. The final result is this. The final result is a differential equation. And you know something about differential equations. Okay? And this will be a differential equation involving derivatives with respect to x. And if you can solve that differential equation, then you will answer the question that we want asked, that we're asking, that we want answered, which is, where is it? Going back up here. If you have an integral, call it I, where the integrand depends on x, depends on y, which is a function of x and its derivative, you want to know what this function y is that either maximizes or minimizes this integral. Both of the problems that I've just introduced, the geodesic problem and the Brakista-Krohn problem, are of this form. Okay, so we're going to derive a general result, and then we're going to answer both of those questions.